Welcome to Power Supply, part of the Fire Alarm and Signaling System Design Fundamentals online learning series from NFPA. Click Next to get started. This learning series covers a range of topics related to fire alarm and signaling system design. By the end of this lesson, you should be able to determine appropriate arrangement for primary power supply to a fire alarm and signaling system, calculate system standby and alarm current for a given system, and apply requirements to determine required capacity of secondary power supply. You can click the button on screen to repeat these navigation instructions. If you're ready to begin, click Next. The menu bar at the top of the window provides important functions to help you as you complete this lesson. Select Menu to see an outline of the lesson that displays your progress. Navigation provides instructions for navigating this lesson. If you need to close the lesson, select Exit to leave and save your progress. Select the collapsed menu icon on the left to show and hide the transcript. This lesson includes knowledge checks and short activities designed to assess and apply your learning along the way. What do you think? Questions give you a chance to think about a topic before we discuss it. Activities ask you to apply what you've learned in a practical scenario. There will be a 10-question assessment at the end of the lesson. You must achieve a passing score to complete this lesson. Remember that what do you think and activity questions are not graded and will not affect your final score. In this lesson, we'll briefly cover the basic considerations for the power supply of a fire alarm and signaling system, then explore basic design considerations through 3 sections: primary power supply requirements, secondary power supply requirements, and an activity where you'll get to apply what you've learned. This lesson should take about 40 minutes to complete. Click Next when you're ready to proceed. Even though there are a few components of a fire alarm and signaling system that don't require power to operate, a total loss of power will always compromise the system. Think about this. A fire occurs in a building with a full fire alarm and signaling system, but no power supply. Some of the devices will partially function. The fire may melt a solder in a heat detector, causing the detector's plunger to drop. But when it makes contact with the exposed conductors inside, nothing will happen. The signal can't be sent. The fire alarm control unit will be off. Occupants can't be notified. Emergency control functions won't be activated to keep them safe, and emergency services won't be contacted. Because a compromised fire alarm and signaling system poses increased dangers to building occupants in the event of an emergency, not only does the system need the appropriate amount of power during normal functioning, but it also needs the appropriate amount during a loss of power. Remember, the goal of the equipment and requirements covered in this lesson is a fully functional fire alarm and signaling system with a constant source of power. In this lesson, we'll use 2 terms: primary power and secondary power. Primary sources provide power during normal operation, and secondary sources provide power during a loss of primary power. The use of both primary and secondary power is the most effective way to ensure that a fire alarm and signaling system has a constant source of power. In most instances, fire alarm and signaling systems will use the local electric utility as their primary power source, while they may also use an engine-driven generator or a cogeneration system. These are less common, however, and must follow stringent requirements for reliability to be considered a primary power source. A common way to ensure reliable power to a fire alarm and signaling system is by supplementing the primary power source, giving the system 2 power supply sources. The secondary source might be batteries or batteries paired with an emergency generator. There's also a way to provide a single power supply source to a fire alarm and signaling system that provides both primary and secondary power. This usually involves a stored energy emergency power supply system, or SEPSS. A fire alarm and signaling system operates in two different modes: standby, when the system is actively monitoring for signals, and alarm, when the system is actively notifying occupants, initiating emergency control functions, or communicating to supervising stations during an emergency. While this can be affected by many different requirements, a standard starting requirement for a fire alarm and signaling systems operation during power loss is 24 hours in standby mode, which is usually long enough to outlast most regular outages, and 5 minutes in alarm mode, which is long enough for a full evacuation in many structures. Both modes are important to consider when calculating the capacity for secondary power, the amount of power required for the continued functioning of a fire alarm and signaling system for a given amount of time after loss of primary power. Unless otherwise noted, all requirements in this lesson are found in NFPA 72, National Fire Alarm and Signaling Code. The requirements covered in this lesson are found in Section 10.6, Power Supplies. Next, we'll begin looking at specific requirements for primary power supply. Earlier, we told you that fire alarm and signaling systems generally use an electric utility for primary power, but they can also use a generator or cogeneration system as a primary power source. Recall that these options aren't common, and they need to meet specific requirements when included in a design. According to NFPA 72, not only do these systems need to be designed and installed in an approved manner, but a person trained in their operation must always be on duty. Another option for primary power is the use of a Stored Energy Power Supply System, or SEPSS. These devices might also be known by other terms. Do you know which of these are common alternate terms for an SEPSS? Select all that you think apply, then click Submit. Sorry, that's incorrect. A Stored Energy Power Supply System may also be called an Energy Storage System, or ESS, or an uninterruptible power supply, or UPS. These systems have three specific designations: type, class, and level. NFPA 72 requires that an SEPSS is type O, or U, class 24, and level 1. This must also be in accordance with NFPA 111, Standard on Stored Electrical Energy Emergency and Standby Power Systems. Let's take a closer look at these designations. The type refers to the interruption between loss of primary power and the start of power flow from the battery. Type O means that there is no interruption, not even 1/4 of a cycle. Type U applies to UPS systems, with the utility as the preferred source. Level 1 equipment must be permanently installed and has performance requirements for the most stringent applications where failure of the equipment to perform could result in loss of human life or serious injury. What do you think? When identifying requirements for an SEPSS, to what does class refer? That's correct. The class determines the minimum time in hours for which an SEPSS is designed to operate at its rated load without being refueled or recharged. For example, a Class 1.5 SEPSS would operate for 1.5 hours, or 90 minutes, and a Class 24 SEPSS, like the kind required by NFPA 72, would operate for 24 hours without being refueled or recharged. Moving back to NFPA 72, it contains requirements for the branch circuit supplying the equipment. What do you think? Which of these other loads are not permitted to be supplied by the same branch circuit supplying the fire alarm and signaling system? Select all that you think apply. Sorry, that's incorrect. None of these are allowed. According to NFPA 72, the branch circuit supplying the fire alarm and signaling system equipment is not permitted to supply any other loads. In addition to the requirement stating that no other loads are permitted on the branch circuit supplying the system, there are other requirements that are important to mention. The circuit and connections must be mechanically protected against damage. The circuit disconnecting means must have a red marking. It must be accessible only to authorized personnel, and it must be marked to identify the system or equipment it serves. The image here shows a red circuit breaker lock that identifies the fire alarm branch circuit and locks it so it cannot be shut off by an unauthorized person, but does not inhibit the circuit breaker from tripping in the case of an overcurrent condition. Finally, a permanent legend inside the fire alarm system control unit must identify the location of the electrical panel board that contains the circuit disconnecting means. As you heard before, even though most fire alarm and signaling systems draw their primary power from an electric utility, there are other options for primary power that are compliant with NFPA 72 and related codes and standards. Their approved usage, however, depends on meeting the strict requirements found in NFPA 72 and those related documents. Next, we'll take a closer look at requirements for the secondary power supply. Recall that the secondary power supply for a fire alarm and signaling system is required to automatically supply energy to the system whenever the primary power supply is not capable of providing the minimum voltage required for proper system operation. A fundamental requirement of secondary power is the amount of time it may take to provide power to a fire alarm and signaling system. NFPA 72 requires that secondary power automatically provide power to the protected premises system within 10 seconds of the loss of primary power. Additionally, it cannot affect the operation of the fire alarm and signaling system when the transfer occurs. Next, we'll explore requirements for two common types of secondary power: generators and batteries. An engine-driven generator provides power to the fire alarm and signaling system via a transfer switch, which transfers power to the generator if there is a loss of primary power. In a previous lesson, you saw requirements for circuit and pathway survivability. If NFPA 72 requires a particular level of survivability for circuits and pathways in a design, equal protection must be provided for power supply circuits. This might include the use of rated cable assemblies or by protecting the circuits in rated enclosures. In a moment, you'll see specific requirements for secondary power supply that's based only on battery energy storage. But keep in mind that even if a design calls for a generator to supply secondary power, a battery backup is still required. However, these batteries are only required to have a capacity of 4 hours. An engine-driven generator that's providing secondary power to a fire alarm and signaling system is itself part of an emergency power supply system. Emergency power supply systems are complex. NFPA 72 does not contain their performance and installation requirements. Instead, it references NFPA 70, National Electrical Code, the NEC, and NFPA 110, Standard for Emergency and Standby Power Systems. What do you think? Which of these statements best describes how codes and standards beyond NFPA 72 inform the performance and installation requirements for emergency power supply systems? That's correct. The performance requirements for emergency power supply systems can be found in NFPA 110, Standard for Emergency and Standby Power Systems, while installation requirements for these and other electrical systems can be found in the NEC. Engine-driven generators used to provide secondary power for a protected premises fire alarm system must comply with NFPA 110 and meet the requirements for a Type 10, Class 24, Level 1 system. The installation of these systems must be in accordance with the NEC, Article 700. Recall the type, class, and level designations we covered earlier. Applying that same information here. Type 10 means that it has a 10-second interruption time. Class 24 means it can run at the rated load for 24 hours without being refueled. And Level 1 means that failure of the equipment to perform could result in loss of human life or serious injuries. A moment ago, we mentioned that systems using engine-driven generators for secondary power supply must also use a battery for secondary power backup, but that this battery is only required to provide 4 hours of capacity. Now, we'll move on to the systems that exclusively use battery energy storage for secondary power supply. NFPA 72 requires that batteries used for secondary power are marked with a date in the month-year format. What do you think? What does this date signify? That's correct. According to NFPA 72, batteries must be marked with the month and year of manufacture. If the battery is not marked with this information by the manufacturer, the installer is responsible for obtaining the date code and marking the battery with the month and year of battery manufacture. The most common type of batteries used for these systems are valve-regulated lead-acid, or VRLA batteries. These batteries are rechargeable, so that they can always be charged when there's primary power. NFPA 72 contains specific requirements for rechargeable batteries. Here are 2 examples. All rechargeable batteries used for a secondary power supply need to be listed and charged by listed means. And the charger needs to be sized so that it can recharge the batteries within 48 hours after being subjected to the load required for the system's capacity. NFPA 72 also requires that battery charging circuits of all systems need to be monitored for failure. What do you think? What signal is produced by a failure of the battery charging circuits and sent to a fire alarm control unit? Sorry, that's incorrect. Being part of the fire alarm and signaling system, the battery charging circuits of all systems are required to be monitored and to produce a trouble signal on failure. As discussed, batteries need to be provided with sufficient capacity to operate the system in an alarm condition, as well as in standby. This design process requires calculating the capacity needs of the system. The required time is based on the type of fire alarm and signaling system, which you can see in this table. For example, according to NFPA 72, battery energy storage used for secondary power supply to an in-building emergency voice alarm system must provide power for 24 hours in standby and 15 minutes in alarm. The extended alarm time is because these systems are in locations with more complex evacuation plans. The voice system would then need to give instructions for evacuation. This would likely take longer than 5 minutes. The necessary battery capacity for a fire alarm and signaling system can be calculated through a 3-step process. First, calculate both the total system standby current and alarm current. Second, calculate both the total system standby capacity and alarm capacity. Third, add the alarm and standby values together and apply required adjustments. Let's walk through each step. Our example will use a small system that contains 1 fire alarm control unit, 4 smoke detectors, and 10 horn strobes. In order to begin, we'll need the standby current and alarm current for all of these devices. What do you think? What's the simplest way to find this information? That's correct. Both the standby current and the alarm current for equipment can be obtained from the manufacturer's datasheet. Consulting the manufacturer's datasheets for the chosen equipment, we found the current requirements in amperes, or amps. The fire alarm control unit uses 0.1 amps in standby and 0.2 amps in alarm. Each smoke detector uses 0.001 amps in standby and 0.05 amps in alarm. Each horn strobe uses 0 amps in standby and 0.075 amps in alarm. Now that we have the necessary standby and alarm current for each device, we can begin the calculation process. Step 1. We need to calculate both the total system standby current and alarm current. We'll achieve this by multiplying the standby current and alarm current for each piece of equipment by the total quantity of each piece of equipment and adding them together. This gives us a total system standby current of 0.104 amps and total system alarm current of 1.15 amps. Next, step 2. We must calculate both the total system standby capacity and alarm capacity. We'll calculate each by using the standby and alarm requirements from NFPA 72. Secondary power supply for this type of system must provide 24 hours of standby and 5 minutes of alarm. Multiplying the total system standby current of 0.104 amps by 24 hours, we calculate a required standby capacity of 2.496 ampere-hours or amp-hours. We'll do the same for the total system alarm current. However, we must convert the 5 minutes of required alarm capacity to hours. 5 minutes is 0.083 hours. Multiplying by the total system alarm current of 1.15 amps, we calculate a required alarm capacity of 0.095 amp-hours. Finally, we can move on to step 3. We need to add the values together and apply any required adjustments. Adding the values together, we find our initial total capacity of 2.59 amp-hours. But we must also apply a safety factor. As batteries age, their ability to provide adequate current diminishes. Battery energy storage used for secondary power supply must meet capacity requirements when the system is new and when the batteries are reaching the end of their service life. By sizing battery energy storage larger than needed during the design phase, you can correct for this. NFPA 72 requires a corrective safety factor of 25%. We apply the safety factor by multiplying the total capacity by 1.25. By doing this, we calculate our required battery capacity of 3.24 amp-hours. Keep in mind that this example was for educational purposes, and battery calculations for a full system are going to be more complex. As systems become larger, the list of equipment will grow. You can view examples of these calculations in a fact sheet available in the Content tab for this lesson in the NFPA Learning Portal. Before you finish this lesson, we'll take you through a short activity. In it, we'll ask you 5 questions about the power supply needs for a fire alarm and signaling system. This fire alarm and signaling system contains a fire alarm control unit, 3 smoke detectors, 2 heat detectors, and 12 speaker strobes. Click Next to get started. Assuming that this system doesn't require any special allowances, which of these options would likely satisfy all NFPA 72 requirements for this system's power needs? Select all that apply. Sorry, that's incorrect. Systems commonly use utility power for their primary power supply, but they still need secondary power. When used for secondary power, a backup generator on its own doesn't meet NFPA 72 requirements. It must be paired with a battery backup. Batteries of sufficient capacity may be used on their own for secondary power. Cogeneration systems are less common, but still compliant with NFPA 72, provided the design includes a secondary power supply. Cogeneration on its own is not compliant. It's been decided that this design will use the local utility for primary power and batteries for secondary power. Now, you need to figure out how large that battery needs to be. What's your first step? That's correct. To determine the necessary size of the batteries used for secondary power, you must first calculate the total system standby current and total system alarm current. You can't calculate the total standby and alarm capacities without these numbers. You also can't apply a safety factor yet. To continue your calculations, you've gathered the manufacturer's data sheets for all of the equipment in the fire alarm and signaling system. For which of these devices will you need to find the standby current and alarm current from the data sheets? Sorry, that's incorrect. You'll need the standby current and alarm current from all of this equipment to continue your calculations. Every device needs to function during loss of primary power to maintain the system's integrity. Once you've calculated the total system standby current and alarm current, you can continue making your capacity calculations. NFPA 72 requires that the secondary power supply for this in-building emergency voice alarm system be able to provide 24 hours of standby and 15 minutes of alarm. Which of these options gives you the proper figures to convert the total system standby current and alarm current to the capacity needs for each mode? Sorry, that's incorrect. You need to multiply the total system standby current and alarm current by the hours required for secondary power to calculate the capacity needs for each mode. The standby requirement, 24 hours, is okay for this calculation, but the alarm requirement, 15 minutes, must first be changed to hours. Therefore, the correct answer is 24 and 0.25. Now that you've calculated the total system standby capacity and alarm capacity needs, you can add them together. This gives you a figure of 2.83 amp hours. Are you ready to finalize your findings and make decisions about the battery energy storage system used in this design? Sorry, that's incorrect. You haven't yet applied the safety factor to the total amp hours you've calculated for this system. Any battery energy storage system you choose will likely degrade over the life of the system. You need to make sure you correct for that by applying the safety factor of 25%. Great job! Applying the 25% safety factor, you've determined the size of the necessary battery energy storage system to be 3.54 amp hours. Now that you've completed this activity, you're almost done with this lesson. Click Next. In this lesson, you learned about basic considerations for the power supply of a fire alarm and signaling system. You should now be able to determine appropriate arrangement for primary power supply to a fire alarm and signaling system, calculate system standby and alarm current for a given system, and apply requirements to determine required capacity of secondary power supply. Thank you for your participation. You may now proceed to the assessment for this lesson. Now it's time to find out what you've learned. You'll be presented with a series of questions. A score of 70% or higher is required to pass. You'll have as many attempts as needed to obtain a passing grade. Note that there is no audio with the assessment questions. Select the next button when you're ready to begin. You have successfully finished the assessment. Once you complete the course evaluation, you will be awarded your certificate of completion with CEUs. You may now exit the module.